Oh, thank you. All right, let's go ahead and get started. Okay, we're going to be starting in on a new unit today, and our first chapter is going to be on what's called thermodynamics. All right, so thermodynamics, kind of broadly speaking, is the study of energy in a chemical reaction. All right, so this is going to be our focus of this chapter, is studying energy in chemical reactions. Energy is one of those things that's a little bit difficult to wrap your head around as a quantity compared to something like mass or volume, because energy shows up in a few different ways, right? So just borrowing from physics, we have our potential energy. If I hold this roll of tape above the desk here, I've given it potential energy above this desktop here. And when I let go of it, that is converted into kinetic energy as it moves through the air, right? So there are these two different forms of energy. And from the universe's standpoint, they're the same thing. They're both energy, but the way that we think about them, the way that we interpret them is very different, okay? So that's what makes energy a little bit hard to wrap your head around. We've discussed energy first last semester, talking about thermal energy, right? So just like analogous to physics and me holding this up above the desk, giving it potential energy, our molecules have this potential energy in them in their chemical bonds, right? There's a bunch of energy stored in those bonds. And when a chemical reaction happens and bonds are being made and broken, that that potential energy stored in those bonds is either absorbed or released in the form of thermal energy. Okay, so if you remember last semester, enthalpy, thermal energy, heat, that sort of business, right? That was our first discussion of energy in chemistry, and we're going to kind of build off that. All right, what we're going to do is lay down what are called the laws of thermodynamics. All right, so first of all, in chemistry, you've probably heard in science, there are no truths, there are only theories, right? But every once in a while, there's a theory that's like 200 years old. Nobody's been able to find any flaw in it whatsoever, so we elevate it to the status of law, right? So these laws of thermodynamics are ancient, like super old, late 1800s theories that nobody's been able to disprove even a little bit yet, right? They seem to really hold up and stand the test of time. Okay, so our first law is also called the conservation of energy principle. All right, and so the first law of thermodynamics states that energy cannot be created or destroyed, only transferred. All right, give me 1 second. Cool. So that first law of thermodynamics, also called the conservation of energy principle, energy cannot be created or destroyed, only transferred, right? So this tape above the desk that has this potential energy, when I let go of it, that energy is transferred into kinetic energy, right? It's not lost, and then it goes into colliding with the table. I had to put a bunch of energy in terms of boiling calories to get it up to that potential energy in the first place, right? So we're just transferring energy through a bunch of different forms. And really what our discussion of today is going to be around is this second law of thermodynamics. All right, and we'll kind of introduce this a little bit more formally later in the class period. For right now, we're just going to start with this observation that the universe hates concentrated energy. All right, so these are these observations that these scientists, and again, we're talking about like 1,800 scientists, where the world of science looked much more like Game of Thrones kind of stuff than it did a room like this, right? There were these libraries, you had like one library in the city, and maybe 10 people in all the city knew how to read. Only one dude could actually read those science books in the library, right? It was a very sort of non-accessible kind of study at that time. And we're talking very early on. The thermometer has just been developed, right? So they're just starting to apply the scientific principle and really understand the world of chemistry. It's crazy how old these theories are, and they still last here, all right? And one of these observations that they've made is that everything, all these chemical processes seem to be dissipating energy. And this is true pretty much at every scale of science. There's going to be a point way long in the future, we're going to be long gone, where every square inch of our universe has the exact same energy density, right? The energy of the entire universe is constantly being spread out to the point where eventually all that energy concentrated in stars is not going to be just located in that one place. Everything's going to be all nice and spread out, okay? Now, we're talking way long in the future, right? Nothing that we got to worry about on our time scale. But nonetheless, there's this observation, all right? And what they want to do, kind of what the goal of those scientists studying thermodynamics want to do, is they want to build a chemical potential. All right, this chemical potential is some measure of whether or not a chemical reaction occurs. Right? This is all the sciences starting out as just a whole bunch of series of observations. We mix two things together. This chemical reaction does happen. We mix two other things together. The chemical reaction doesn't happen. Like, what are the rules here? Right? That's the goal, is to try to figure this out. Is there some energy source that we can measure that's going to tell us whether or not a chemical reaction will actually occur? Okay, and so what they're going to start with is that first source of energy that they stumbled upon, that delta H enthalpy. All right, so they're going to say, all right, this chemical potential, I know it has to be in some way related to enthalpy, delta H. All right? There's just something missing here. There's some missing component to our chemical potential that we need to figure out. Cool. So before we discuss what's missing here, let's review what we mean by enthalpy. All right, this quantity, enthalpy, we use this symbol delta H for. Okay, enthalpy is a measure of the thermal energy, also just called heat, that is absorbed or released by a chemical process. All right, so scientists, they, again, late 1800s, they've just developed that new fancy thermometer. So they're studying these reactions, they're measuring these temperature changes that occur, and they're relating it back to this source of energy we call enthalpy, right? The thermal energy that is absorbed or released by a chemical process. Okay, so we got some fancy terminology here. When delta H is less than 0, right? So delta H has a negative value. We call those reactions exothermic. And that means that they release heat. Okay, when delta H is greater than 0. Does anybody remember what we call these ones? Endothermic. All right, and these are reactions that absorb heat. All right, so these early chemists, they have stumbled upon this new source of energy here, right? Our thermal energy we call enthalpy. And again, they're trying to build this chemical potential. And they're like, all right, I know this enthalpy business is going to be involved somewhere. All right? And that's just based on this very simple observation that most chemical reactions, or we can even say chemical processes, are exothermic. Right? So it just seems like there's something very favorable about something that releases thermal energy. That seems to be good from the universe's standpoint here. Most of these reactions that they're studying in their lab are reactions that release thermal energy. All right? But they don't want a chemical potential that works most of the time, right? They want something that works all the time. And again, we got this caveat, most here. So they start focusing in on some of these endothermic processes. So let's take a look at one in particular that was giving them trouble, and that is the melting of ice. All right, so if we want to put this in a chemical equation, that means we're going to take solid H2O, turn it into liquid H2O. Okay, so has anybody seen ice melt before? Great, so we know it happens, right? This isn't something that's like in complete violation of universal rules or something like that. Definitely something that we know actually occurs. The troubling thing, or at least the confusing thing, is that our delta H is definitely going to be greater than 0 here. All right, this reaction would be endothermic. All right, that's because H2O solid has to absorb heat. To convert to the liquid water molecules. All right, remember what temperature is doing, what heat is doing is increasing the kinetic energy of those molecules, while solids, they're stuck in place. In the liquid state, they have much more kinetic energy. They're moving around much more. And so in order to get that extra kinetic energy, they have to absorb heat. So this process here, we know actually occurs, but it's one of these rare endothermic processes. Okay? So what they sort of are noticing when they're studying all these endothermic processes is they all seem to have one common feature, which is that you start out with some ordered substance, right? Our solid has a lot of order associated with it. All those water molecules are in specific places. Their neighbors aren't changing. There's just a lot of structure to that solid. And when it melts, we create a more disordered state. All right, and so this melting of ice and all these endothermic processes that they observe occurring, they are all processes that create disorder. All right, so then this leads them to this new source of energy that is much more difficult to kind of wrap your head around and to measure. But nonetheless, I'm going to try to convince you all here today actually exists what's called entropy. Bless you.
Thank you.
All right, so first of all, the definition, the very wonky chemistry definition of entropy is the number of chemically equivalent ways to arrange a system. Okay, so what the heck does that mean? All right, this is kind of a very statistical mechanics way of defining entropy, which is great for that course that you're going to take in your last year of being a chemistry major, but for our purposes, it's not the most helpful definition. It's a little bit too wonky for us, so we're going to use kind of a simplified definition here. All right, entropy is a measure of the universe's energetic push towards disorder. All right, so that is not necessarily all that much more clarifying, right? That sounds pretty weird here. It turns out, and again, this is what we're going to try to think about today, that the universe has this energy that's dedicated to creating a more disordered state. Things that create disorder, processes that create disorder are more energetically favorable. You can go in and measure this energy, all right? So we got this push towards disorder going on. Let's think about something very simple, not even a chemistry kind of thing. All right. Like if we break a drinking glass. Like let's say that we take our drinking glass or one of the beakers in the lab, and all of a sudden it gets bumped off the table, and all of a sudden it's shattered into a bunch of different pieces. Okay? So first of all, just thinking about entropy here, would this be something that creates order or more disorder? Disorder, right? We've taken this very ordered drinking glass and then we shattered it into a bunch of pieces here. So this would be an entropically favorable process, okay? So let's just note here, this way would be entropically favorable. Now, if I tried to pick up all those pieces and arrange them back into that drinking glass, would I be creating more order or more disorder? Now I'd be creating more order, so that would be entropically unfavorable. All right, and if we want to think about it from our definition here, right, how many ways could you shatter a drinking glass? Right? If you knock it off the table, that event of breaking that glass could mean one of like 100 different, even more, a bajillion different things from devils in the details. How many pieces? How big are the pieces? What are the shape of the pieces? All of those would constitute shattering that drinking glass into this disordered state. If we took all those pieces and we tried to build that drinking glass back up, how many ways could we do it? There'd only be one. There'd only be one way to put those pieces together. I mean, maybe the pieces just happen to break and be the exact same, so there are two of them that are interchangeable, but even that would be pretty rare, right? So to assemble all of this back into that ordered state, there's really only one way to do it, okay? And so the universe, again, has this energy that pushes things towards these disordered states, okay? One of the reasons why this is so difficult for us to wrap our heads around is we live in a very ordered environment, right? Human life is incredibly ordered. We look around right now. It's not like we're sitting in a pile of rubble. We have a bunch of boards in place with nails in specific places. Us ourselves are incredibly ordered beings. Right? We have cells in specific places. They've got specific enzymes to doing specific jobs. Our heart cells are different from our lung cells, all that stuff, right? So it's kind of like, well, what are you talking about? We look around here and we see a lot of order going on in this room right now, right? But we're talking from a grand scale. And let's think about it here. How much life have we found out there in the universe, right? At least it seems to be a pretty rare frickin' event here. Everything had to go right just for us to be here, right? The right temperature, the right moisture content. There are a lot of other rocks floating around out there around a lot of other suns, and we have yet to find one that has life on it. So we are really an exception to the universe's push towards disorder. If you go looking around the universe, most places aren't nice and neat and ordered like this, right? Not only that, but we have this beautiful building here. Well, we got a lot of weather patterns. I mean, why do we have a building to begin with? Why aren't we just sitting outside? Because we have to deal with all these weather patterns that are going through here. A tornado or an earthquake or something runs through here. It's going to take this nice ordered structure and turn it into a pile of disorder, right? And the reverse doesn't happen, right? Nobody's chilling in Tornado Alley where a tornado comes through and then builds a house out of a pile of sticks, right? The other way never occurs. So there's this big energetic push towards more disordered states, and we call that entropy, okay? So what we're going to do is we're going to take a look at a few processes and try to think about them just from an entropy standpoint here. All right, let's look at the condensing of water vapor. All right, and I lied. Before we do that, I got to introduce some fancy terminology here. Just like we have fancy terms for delta H, whether it's positive or negative, we have something similar for delta S. Okay, when delta S is a positive value, is greater than 0, we call that entropically favorable. Okay, and by entropically favorable, we mean it creates disorder. All right, likewise, if we had a negative entropy, we would call that entropically unfavorable. That would be a process that creates order. Okay, so what we're going to do is we're going to take a look at a bunch of different processes, and we want to think about the sign of delta S. Think about whether they're entropically favorable or unfavorable, i.e. creating order or more disorder. Cool. All right, so condensing of water vapor. That means that we have gaseous water being condensed into liquid water. Okay, and from an entropy standpoint, my delta S, what do we think? Is this going to be entropically favorable or unfavorable? Are we creating more order or more disorder here? So the gas is a much more disordered state than a liquid, right? Because in a gas, those molecules are now floating around in 3 dimensions, crashing all over the place. In a liquid state, they're interacting much more strongly with one another. Their neighbors aren't changing as quickly. They have less kinetic energy. So yes, this would be an example of delta S being less than 0 or entropically unfavorable. Okay, I'm going to leave some room for some new examples, but I am going to start a list here of factors that affect entropy. All right, and so that first one are our states of matter. This has an enormous impact on entropy. A gas is a much more entropically favorable state than a liquid, than a solid. All right, let's take a look at a chemical reaction here. We're going to take dinitrogen tetraoxide gas, and we're going to convert it into 2 molecules of nitrogen dioxide gas. All right, and this one's a little bit harder to see here because if we look, they're both gases, so we don't have that state of matter to look at. But what we want to look at here is that we have one gas particle that we're decomposing, we're breaking it up into 2 gas particles. So what's our more disordered state? One big molecule floating around or 2 small ones floating around independent of one another? The 2 little ones, right? So anytime you take something big and break it up into a bunch of little pieces, that is an entropically favorable process. Meaning our delta S would be a positive value. All right, so we're making an ordered list here. So definitely the most important factor for predicting entropy are just those states of matter. All right, but another important one is number of particles. Okay, more particles is more entropically favorable than fewer particles. All right, what about if we create a solution? meaning I take something like solid sodium chloride. All right, and I'm going to break it into sodium ions and chloride ions. Yeah, so when we have our sodium and our chloride stuck together in that formula unit, that's a very ordered state. When we make a solution with it, now they're floating around independent of one another. So this process here would be entropically favorable, right? That positive delta S value. All right, so on our list, we're going to add here creating a solution. We're going to put a little asterisk next to it, because this one we need to discuss a little more. All right, turns out devil's in the details. That is generally true, creating a solution. There is a little bit more going on that we want to talk about as well, but we'll kick that discussion down the road a little bit. Okay. All right, what about temperature effects? Let's say that I have carbon dioxide gas at a temperature of 100 degrees Celsius, and I cool it down such that now it's at 20 degrees Celsius. All right? So again, we want to remember what exactly temperature is doing for us at that molecular level. It indicates the kinetic energy of those gas molecules, how fast they're moving around. So what's going to be a more disordered state? Gas molecules moving around quickly or moving around slowly? Yeah, the hot gas is going to be our more disordered state. So now we're going from disordered to ordered or entropically unfavorable. Okay, so on our list, we're going to add temperature. All right, an increased temperature, more disordered than a decreased temperature. All right, and lastly, and this is a pretty minor effect, but nonetheless, there is an effect of volume on our gas's entropy as well. The larger the volume, the more entropy. All right, and this actually is more helpful to think about that wonky definition of entropy, the number of chemically equivalent ways to arrange a system. Well, if you have more volume, there's more chemically equivalent ways for you to arrange those gas molecules inside that same volume. But this list is ordered here. By far the most important factor is that state of matter. All right, then number of particles. Those two alone are usually pretty good for predicting whether or not a reaction is entropically favorable or unfavorable, but also creating a solution. Increases in temperature, this is going to be important to think about as well. And then last on our list here being volume. Cool. All right, so they're going to go back here. They're like, all right, we got a theory here about what should be our second law. They propose a theory that now is known as the second law of thermodynamics. So let's just go formalize that. We kind of started out with that simple observation. All right, our formal definition of our second law of thermodynamics is that all chemical processes increase the entropy of the universe. All right, so we can say that same thing by saying that the delta S of the universe has to be greater than 0. That's the rule. Cool. All right, we'll build off this in a second. For right now, we're going to I'm going to put down a few chemical reactions, and I want you to look at them and classify them as being entropically favorable or unfavorable. All right, so this first reaction here, what do we think? Entropically favorable or unfavorable? Yeah, so this would be entropically unfavorable. All right, awesome, because of our number of particles, right? We have all gases involved here, so our state of matter isn't what's going to make the difference. It's the fact that we have 4 gas particles being combined into just 2 gas particles. That is an entropically unfavorable event or has a negative delta S. All right, well, what about this next reaction here? What type of reaction is this? Precipitation reaction. So these precipitation reactions, are they entropically favorable or unfavorable? They're also entropically unfavorable because we get these 2 nice disordered solutions where all those ions are moving around independently, and now all of a sudden we're going to form this solid precipitate, which is this ordered state here. All right. Now, both of these reactions are entropically unfavorable, but both of them do occur. All right, these are both reactions that if we mix together fluorine and nitrogen, we would produce nitrogen trifluoride. Likewise, last semester, you guys mixed together silver nitrate and sodium chloride and produced solid silver chloride. So these 2 reactions do indeed occur. So how do we square that away with our second law of thermodynamics, which says that the delta S of the universe has to be greater than 0? Okay, well, importantly, 2 other important observations to make about these reactions is that both of them are also exothermic. All right, both of these reactions here have a negative delta H value, meaning that heat is released when this reaction occurs. All right, so this observation here is what leads them to be able to build that chemical potential that we were after, right? We said that we had this chemical potential. We knew that enthalpy was going to be an important part. We got something missing here. We know now that that's entropy, but how do these two combine to make our chemical potential? All right, so now what we're going to do is derive that chemical potential. Okay, so we're going to start with that delta S of our universe has to be greater than 0, right? That's our second law of thermodynamics. All right, well, the delta S of the universe we can divide into two parts. What we call the system and the surroundings. All right, the system is what you're studying. Since this is a chemistry class, that is typically a chemical process, either a reaction or a phase change. And the surroundings are quite literally everything else. All right, so if we mix together sodium nitrate and, silver nitrate and sodium chloride in a beaker, right, the system is going to be those solutions, that chemical reaction that's taking place, and the surroundings are going to be everything else. The beaker, the scientist, the room, the building, literally everything else is going to be lumped into that category of the surroundings. All right? So, if that second law is true, and our delta S of our system is less than 0, right? As in the case of these reactions here, these have delta S's less than 0, but we know they occur. All right, then that simply means that the other component here, the surroundings, have to be bigger, right? The only way that the system is allowed to be less than 0, but this whole thing work out to be a positive value, is if the surroundings are larger, right? So that would mean that the delta S of our surroundings is greater than the delta S of our system in magnitude. All right. And the way that they were able to circle this square here is by establishing that the delta S of the surroundings is equal to the delta H of the system divided by negative T. All right, and so importantly, what this equation here is saying is if a process is exothermic, if it releases thermal energy, then it increases the entropy of the surroundings. All right, that's what my equation here is telling me. So if we're studying this reaction here, even though this reaction is entropically unfavorable, it's still allowed to happen because it's exothermic. So when it happens, it releases thermal energy, and that thermal energy increases the entropy of the surroundings, right? We talked about how increasing temperature will lead to increases in entropy, all right? We got a lot of processes that happen in our body that are not entropically favorable, right? The building of enzymes, the building of those large DNA molecules that store your genetic code. These are all entropically unfavorable events. So how does the body get away with doing them? Well, it pairs them up with processes that are going to release thermal energy, burn some calories, which will then help increase the entropy of the surroundings. Okay, so what we're going to do is plug everything back in to our equation up here. We're going to turn around and plug our surroundings term back in. So now we have delta S of the universe equals delta S of the system minus delta H of the system over T. All right, and they could have stopped here, but they didn't like this equation as is because entropy is measured not in units of energy all by itself, but energy per Kelvin, so joules per Kelvin. So instead, what they want to do to make it an energy is they're going to take everything and multiply it by negative T. All right, so we get negative T delta S of the universe equals negative T delta S plus delta H of our system. All right, and we're just going to rearrange this to put it in the form that we're used to seeing here, okay, as well as define what we call our chemical potential, our delta G. So delta G equals delta H minus T delta S. All right, this is our equation for our chemical potential. All right, named after the guy who established this, this is what we call, that delta G is what we call our Gibbs free energy. All right, and again, this is our measure of whether or not something can happen because it's equal to negative T times the delta S of the universe. And the delta S of the universe has to be positive. That means that if delta G is less than 0, this is what we would call a spontaneous process. Or we can more fancily call it an exergonic process. All right, which simply means that it will occur. Or if delta G is a positive value, that's what we call a non-spontaneous or endergonic process. meaning it will not occur. Cool. So we built our chemical potential. This is an energy that we can measure, and this energy will tell us whether or not that chemical process will actually occur. If we measure that energy and we get a negative value, that means it will occur. We call that a spontaneous reaction or an exergonic reaction. If that delta G is a positive value, that process will not occur, meaning that it's non-spontaneous or endergonic. All right, so now what we want to do is we want to look carefully at this formula here, and we're going to build ourselves a little bit of a cheat sheet. All right, where we're going to look at the sign of delta G, delta H, and delta S, and try to figure out what their relationship is. All right, so what exactly do I mean by that? Well, let's imagine that we have an exothermic reaction. That means that delta H is negative. That is also entropically favorable. So that delta S is positive. All right, well, let's look carefully at our equation here and try to figure out what the sign of delta G would be. All right, if we plugged in a negative value for enthalpy and a positive value for entropy, well, then I would take my enthalpy and I would add, what's going to happen when we multiply that positive value by negative T? It's going to be turned into a negative number, and a negative number plus a negative number is also a negative number. All right, so if this process was both exothermic and entropically favorable, then it would have to be spontaneous. Have a negative value for delta G. All right, and this first line is kind of important to commit to memory here. If a process is both exothermic and entropically favorable, that's like a double winner from the universe's standpoint, right? The universe is like, man, you're telling me not only does this release heat, which I really love, but it also increases the disorder. I also love that. That's a win-win, all right? So a negative delta H is good, a positive delta S is good, and a negative delta G is good, right? That's a reaction that will happen. Okay, a great example of a reaction that's both exothermic and entropically favorable is the combustion of gasoline. That is a process that creates a lot of tiny gas molecules, so it's very entropically favorable. It also releases a ton of heat, so it's very exothermic. That's why we've gotten kind of addicted to those combustion reactions to create energy, because they're favorable from both of those sources of energy, making them very favorable to occur. Let's think about the flip side here. What if we have an endothermic reaction that is entropically unfavorable? All right, let's go back and plug in some values here, some signs. Now we got a positive delta H and a negative delta S. That means I'm going to take that positive delta H and I'm going to add my negative number times a negative number, gives me a positive number. And so delta G then is going to have to be positive. All right, so if you have a process that is both endothermic and entropically unfavorable, not going to happen. Right? From the universe's standpoint, double loser. Not only does it create order, which the universe doesn't like, it also absorbs heat, which the universe doesn't like. Not going to let it happen. All right, but now let's think, so in both of these examples, my entropy and my enthalpy are in agreement with one another, right? In the first example, they're both favorable. In the second example, they're both unfavorable. But what if there's like this conflict between the two of them? What if we had a process that was exothermic, but entropically unfavorable? All right, so good from an enthalpy standpoint, but bad from an entropy standpoint. All right, well, if we plug in values here, that one's negative, delta S is negative, but now I have this negative number plus this positive number when I multiply it by that negative t. All right, so then what's the sign of delta G going to be if we take a negative number and we add a positive number? It's going to depend which is greater. Exactly, right? So is this a big positive number or is it a little positive number, right? Devil's going to be in the details here. Okay, so what we want to note is that our entropy term is dependent on the temperature of the system as well. All right, so let's imagine that we plug in some tiny number for temperature so that I just have a little positive value for my entropy here. Well, that means that at that low temperature, my enthalpy term is going to dominate, and that reaction will be spontaneous. So at low temperatures, we would get a negative delta G, or a spontaneous reaction. All right, but now let's do the same thing, but we're going to crank up that temperature so that now it's a very large term, that purple term. Well, that at high temperatures would give us a positive delta G, or be non-spontaneous. All right, so a good example of this would be that reaction that we were taking a look at, right? This would be an example of something that's entropically unfavorable but exothermic, which means that if we turn up the temperature enough, we would eventually find that this reaction would no longer be spontaneous. Right? It's apparently something that's allowed to occur at lower temperatures, but not at higher temperatures. Another example that we took a look at was the condensing of water vapor. This was also entropically unfavorable, but we can note it's going to be exothermic. All right? Because those gas molecules are going to have to release some thermal energy in order to make their way into the liquid state, right? They got to give up some of that kinetic energy in order to become liquids. This condensation reaction is something that will occur when it's cold, right? But if it's really hot out there, then all of a sudden you won't get this reaction occurring. All right, and then lastly, last situation here would be if a reaction was endothermic, but entropically favorable. All right, and here we would find the exact opposite. We would find that at low temperatures, this reaction would not be allowed to occur, non-spontaneous. All right, but if we went to high enough temperatures, all of a sudden it would become a spontaneous process. All right, and we saw a great example of this at the very beginning of the day. That was that very first endothermic process that we looked at, the melting of ice. This is a process that is endothermic but creates disorder. So our delta S of this process is greater than 0. All right, and this is a process that apparently, according to our cheat sheet, should be spontaneous at high temperatures but not at low temperatures. Is that our experience with ice? Does it melt spontaneously when it's cold or when it's hot? When it's hot, right? So it will melt as long as it's above its temperature, but you can go low enough where this process will no longer happen, right? So once you get to a certain cold temperature, your ice is not going to spontaneously melt. But if you get the temperature high enough, all of a sudden that melting process becomes spontaneous, right? And that's because it's got a mix of being endothermic but entropically favorable. Cool. All right, so we're going to sort of get all teed up for next lecture here by talking about what's called Hess's law. All right, Hess's law is when we can combine known chemical reactions and their thermodynamic variables to study new reactions. All right, and there is this whole appendix we're going to see in a second of known chemical reactions called formation reactions. All right, so let's take a look at one of these formation reactions. All right, we're going to have some compound as our product. So for example, nitrogen dioxide gas. All right, that's going to be our compound is our product of our formation reaction. Your reactants in these formation reactions are every element in their standard state, every element in that compound. All right, so what do I mean by that? I'm going to look at my compound formula here. We have a nitrogen and an oxygen, so I'm going to list those two elements. But in their standard states, they are both diatomic gases. Right, so I have this synthesis reaction here of each element in their standard state. And the thing that's going to make these a little weird, but we're going to see it makes these reactions super useful to use, is that we're going to balance such that our product has a coefficient of 1. All right, so I'm going to force the coefficient on my product side to be a 1. All right, which means that I'm going to have to use this half integer to balance my nitrogens on my reactant side. Okay, so let's do another one very similar here. See if you can't give me the formation reaction of dinitrogen tetraoxide. All right, we got those same two elements in their standard state. We just need to balance such that that coefficient on our product side is a 1. Cool. All right, so then what's the deal with these reactions? Why do we care about these formation reactions? Well, again, these are known reactions, and we can combine them to study new reactions. And what do I mean by their known reactions? Well, if we go to our constants page for this chapter, we see this big list here, this appendix, which is a giant list of all of our thermodynamic variables, our delta H, delta G, and entropy. All right, and if we look carefully, they have these little F's next to them because these are the formation reaction values. So if I go and I look up my compound, let's zoom out. Let's find nitrogen. Here we go. All right, notice that there's 2 dinitrogen tetraoxides. Which one am I going to look at? The gas, right? We want that exact match. Well, what's listed here are enthalpy, free energy, and entropy values, and they specifically correspond to those formation reactions, right? So the delta G of that formation reaction, whoops, not that, is that 99.8 kilojoules per mole. All right, so first of all, that's cool in and of itself. I got this random chemical reaction, and I can look up all of its thermodynamic variables. I'm just going to use delta G as an example here. Would we say that this reaction is spontaneous or non-spontaneous? This would be a non-spontaneous reaction according to my delta G value because it's positive. All right. I can do the same thing for this compound as well. I got to look up my nitrogen dioxide gas on my table. All right, and that middle column is again my delta G value. So this tells me that that formation reaction has a delta G of 51.3. And those units are kilojoules per mole. So this reaction is also non-spontaneous. All right, but what we're going to see next time is, again, what we're going to be able to do is combine these two reactions together, all right, to study a new reaction. All right, one we know nothing about here, where our two nitrogen dioxides get converted to dinitrogen tetraoxide. Okay, and what we're going to be able to do is combine these two known reactions together to figure out what the delta G is of that reaction. All right, we did this last semester as well, with specifically only with those enthalpy values. All right, this is known as Hess's law, and that's where we'll pick up next time. Cool. All right, we'll take our break. We will meet back here at half after for our lab.